In this lecture, we are going to start a new concept which is called random variables. Before starting this, that I got some feedback that it would be helpful if I use the class note instead of the slides. The reason being told that well, the example numbers are different in slide and the class note, so it become little difficult for some of the students to understand which uh, example or which theorem or which remark I am talking about, I am referring to. That's why this feedback I got. So from now onwards, I will use the uh, lecture note instead of the slides. Okay, so let us start with random variable. So so random variable, what is random variable and why it is important? Let us discuss these things first. So you see that when we are talking about the probabilities, we talk about the probability of different events, and if an event is nothing but sets in the sigma field. So now in most of the practical scenarios, we are mainly talk about some numerical characteristics of a random experiment. For example, as I talked, I have written here that we may be interested in the number of heads out of 10 tosses of a coin. We may be interested in the number of bugs that is reported for a newly developed software, or we may be interested in the total yield of a particular crop in a particular part of India, for example, in the state Assam or some other part of India. We may be interested in level of water in a river, maybe in the Brahmaputra river, especially during the flood, during the rainy season, during the flood. Okay, so in all those things, you see that we are mainly talking about some numerical characteristics. We may be interested in weight of a person, we may be interested in the height of a person, we may be interested in income of a person, savings of a person, or anything. Most of the thing you can see that they are some numerical characteristics. So most of the cases, it is much more meaningful to talk about some numerical values rather than some very random, very abstract sets. Okay, rather than some abstract sets. And random variable actually do this one. So what random variable do? Random variable maps the sample space, any arbitrary sample space, to the real number. So now if I have a mapping from a arbitrary sample space to real number, so the outcome of the mapping is basically a real number. So that is a numerical characteristic. Okay. So so that random variable in the discussion of the probability comes very naturally, because most of the cases we are talking about numerical characteristics rather than very abstract sets. One reason is this, and another mathematical reason behind this random variable is as follows. Note that in your math course or in your different courses, you have learned lot of tools which can be applied on the real number. For example, you know derivative, you know integration, you know several property of the real line, several property of in general r to the power n. So if I can map the abstract sample space to R, I can use those numerical characteristics here and I can analyze the situation. So so that's why the random variable is important because of two reasons. One of them is it is a very natural thing to consider for the practical scenario, and the another thing is that we have a lot of mathematical tools on R, so we can use those tools to analyze the probabilistic characteristic of a random variable. Okay, so it is the use is two-folded. One is practical point of view, and another is mathematical point of view. So let us start with what is the definition of the random variable. So definition of the random variable is quite simple. It says that any function from S to R, any function x from S to R is called a random variable. Okay, So if I take any function from x to r, it will turns out to be a random variable. So let us consider the scenario like that. So basically, random variable. The definition of the random variable is that any function x from the sample space to R is a random variable. So let us talk about some examples. So the first example, example 2.1. In the example 2.1, we toss a coin n times. Toss a coin n times. So in this case, I can able to write what is the sample space. So sample space in this case is nothing but of the form x1, x2 in this way up to xn, where all the xi's belongs to either head or not or tail. All the xi either head or tail, and I equals to 1, 2 up to n. So clearly this set S has how many points? The set S has 2 to the power n points. Okay. So in this case, I have a sample space where the sample space is basically nothing but kind of a n tuples of head or tail. And in this case, suppose I am not interested exactly what is the order of coming head and tail, but I am interested in only the number of heads out of the entrance. So I can define a random variable x of omega, which is basically nothing but number of heads, number of heads in omega, and omega is of the form obviously x1 to xn, where x1 to xn, all of them are either head or tail. So clearly this x is a function from the sample space to R, so this x is a random variable, hence this is a random variable. Okay, so in this case I am interested only in the number of heads. I am only interested in the number of heads. So the number of heads, the function which maps each point in the sample space to the number of heads in that particular sample point, particular elementary event is basically a random variable, and we are going to talk about, for example, in this example, about this random variable. Similarly, you can take number of tails here also, which I have actually mentioned in the example 2.1 in the class note, but I deliberately changed it to head so that you can understand different scenarios. Okay, so now you see that, okay, for simplicity, let us take n equals to 2. The reason is basically nothing but I do not want to write so many head and tails. I am just want to give you a simple example. So take n equals to 2. So that basically means my s is basically of the form x1, x2, where x1 and x2 both belongs to the set head and tail, and sample space having the sample space has how many points? 4 points. Okay. And suppose that in this case I take all the points are equally likely. So I take the head has same value with tail has same value as with tail has the same value as probability of tail head, which is equals to 1 by 4. This is 1 by 4 because sum has to be 1. Okay, now suppose in this case I try to find out what is the probability that x equals to 0. Suppose I try to find out what is the probability that x equals to 0. Now see that x equals to 0 if and only if I have the point tail. Number of head is 0 if and only if I observe that tail has occurred. Both the results of both the tosses are tail. So that means the probability of 0 is nothing but probability of tail and I know the probability of tell which is 1 by 4, so I can able to find out what is the probability of x equals to 0. Similarly, if I try to find out what is the probability of x equals to 2, note that x equals to 2 if and only if I observe head and head in both the tosses. So that means this probability is same as head head, which is again 1 by 4. Now, if I try to find out what is the probability x equals to 1, you see that x equals to 1 can occur in two cases: if I observe head and tail, or if I observe tail and head. So probability head tail or tail head, if this thing happens, then I have x equals to 1. So that means probability of x equals to 1 is either head tail or tail head, which is basically mean union. And because these two elementary events are disjoint, so I can write this quantity is probability of head tail plus probability of tail head, and this probability turns out to be 1 by 2. Now note that intuition tells that x can take values. I mean, not intuition, actually this x can take values, in this case any of these three values, 0, 1 and 2. And so that means basically I have calculated the probability of all possible values of x, and we can easily see that x equals to 0 plus probability that x equals to 1 plus probability that x equals to 2, that turns out to be 1, and that should be the case because x can take these three values. So if I add up all the possible probability of all the possible values, then that should be 1. It is basically same as the probability of the sample space. Okay, and so that means basically I can find out the probability of x taking different values if I know the probability assignment on the sample space. Okay, probability assignment on the sample space, rather not sample space, the sigma field over the sample space. If I know the probability assignment on the sigma field over the sample space, I can find out what is the probabilities of x taking different values. And note that how can I find it out? The basic idea is nothing but when I try to find out what is the probability of 0, I actually find out what is the inverse mapping of the fact that x equals to 0. Okay, I basically find out what is the x inverse 0, and x inverse 0 is basically tail. So probability of x equals to 0 is basically probability of x inverse 0, which is tail, and then I find out the probability. Similarly, in this case also, that x inverse 1 is basically head tail or tail head. That's why the probability x equals to 1 is probability of head tail or tail head, and from that I can able to find out the probability. And thus you see that the same thing I can do it for any general value of n, but obviously that this calculation will be quite complicated. Obviously that if I take any general value of n, the finding out the probability of x equals to 0 and x equals to n is fairly simple, but when I try to find out maybe x equals to something in between 0 and 1, the computation could be little different. Computation will be little different. Okay, let us consider another example. So example number 2.2, example number 2.2, and in this case, what I am doing is that the random experiment is rolling a die 2 times. Rolling a die 2 times. Okay, if I roll a die 2 times, it is very easy to see that the sample space having the points like this, where I equals to 1 2 up to 6 and j equals to 1 2 up to 6, and clearly this s has 36 points. And suppose I take that the probability of any elementary events is 1 by 36 for all ij belongs to S. Okay, in this case, maybe I can talk about a random variable x of ij is equals to, let us take, let assume this quantity is equals to I plus j. So that means basically nothing but I roll the die twice and I sum up the outcome. Take the sum of the outcome. Clearly, in this case, x is a function from S to R, and hence x is a random variable. Implies that x is a random variable. Okay, and you see that again I can find out the probabilities of different the different values of x. For example, if I try to find out what is the probability that x equals to, okay, before going into finding out the values of probability that x equals to x, first note that the values of x ij belongs to, or I should write in this way, the not values of that is a better way to write. Note that the range of x, because x is a function, so I have a range of x. The range of x is nothing but 2, 3, so on and so forth, up to 12. And now I can find out what is the probability of 2. I can find out what is the probability x equals to 3, so on x equals to 12. And to find out x equals to 2, it is basically nothing but 1 comma 1. Both the outcomes are 1. Then I can have x equals to 2. So this probability is basically 1 by 36. Then I can find out what is the probability that x equals to 3, and this can happen either 1 2 or 2 1. So this probability is 2 by 36, and so on and so forth. You can find out what are the different probabilities of x equals to x for different x in this set, for different for xi, and so on. In this way, in this manner, we can calculate probability of x, capital X equals to small x for all x small x belongs to the set 2, 3, and so on up to 12. Okay, note that it is a general practice that we are going to use capital letter for random variable and small letter to signify a value of the random variable. So capital X equals to small x, that basically means that the random variable capital X takes the value x. So in this particular case, the small x is 2. In this particular case, the small x is 3, and so on and so forth. So this particular practice we will use, and this is a very very standard practice in any book, anywhere you will find this practice, that random variables are denoted by the capital letters, whereas the values of the random variables are denoted by the small letters. Okay, so in this manner, actually, you will be able to find out the different probabilities for this example, and you can check that these probabilities are given by this thing. So, for example, if you try to find out what is the probability that x equals to 8, that means what is the probability that sum is 8, then you will be able to find out that there are 5 possibilities such that sum is 8, so the probability is 5 by 36. Okay, so this way we can proceed. Next example, example 2.3. So example 2.3 is little bit of different thing. So here we are talking about testing of some product. So testing of some product. So maybe I can talk about product, maybe bulb. Okay, testing of some product, maybe I am talking about bulb. Bulb is just for example. You can talk about any product. Maybe I can talk about a computer monitor. I can talk about mobile phone. I can talk about any product like this. Okay, electronic products or any mechanical products, anything. So what happens in this kind of testing? This kind of testing is generally called reliability testing. So in a real reliability testing, from the name it is clear that I am going to test how reliable the product is. So in most of the cases, in most of the typical reliability experiment, the experimenter want to know define numerical characteristics of a product. So for example, if I talk about bulb, I may be interested to know what is the average lifetime of a bulb manufactured by a company. It is more meaningful if I talk about some electronic products, for example, a particular model of a mobile. I may want to know for a particular model of a mobile what is the average lifetime of the battery of that particular mobile. Because it's a quite important thing. If the average lifetime is long, then it is much better for the customer point of view. On the other hand, if the average lifetime is short, then it is not good for the customer's point of view. If the price is fixed. Okay, so these reliability things are quite important in practice, and there are a lot of practical use of the reliability experiment. So now note that if I want to do such kind of experiment, maybe if I want to know what is the average lifetime of bulb, what I have to do? I have to take some bulb, maybe 50 bulbs, and I have to put all the bulbs on the test, and I have to wait till the bulbs fail, and I need to basically note down when the bulbs are failing. So I will note down that the first bulb failed after 3 days of use, second bulb failed after 10 days of use, the third bulb fails after 1 month of use, and so on and so forth. In this way, I will not note down the failure time. So when I note down this failure times is basically nothing but the lifetime of the bulb. Now, this lifetime of the bulb is a numerical number. Is a number. Is a real number. So clearly, in this case, I have a mapping. I have real number. So I can talk about real number. I can talk about this what is called this random variable in this case. So so that basically means the experiment is noting down. The experiment is the random. The random experiment is to put the bulbs on a test and note down the failure times, right? And note down the failure time. And when I note down the failure time, the sample space become 0 to infinity, because lifetimes are generally more than 0. So the sample space becomes 0 to infinity. Maybe I can have a upper bound, but I'm not writing the upper bound exactly, because that exact upper bound I do not know. That a bulb can work for a very long period of time. So I can take the sample space is 0 to infinity. So in this case, I am interested in lifetime itself. I can consider a mapping take if we are interested in lifetime itself. We may take we may take x1 from S to R, defined by the identity mapping that x1 omega is equals to omega, and that basically identity mapping. And clearly this x1 is a random variable. Okay, so note that there is a basic difference in with x1 compared to the previous two the random variable in the previous two examples. See, in both the example, in the example 2.1 as well as 2.2, The random variables can take some distinct values, like in the first example, it is 0, 2, 0, 1, and 2. In the second example, it can take values 2, 3, up to 12. So there are 11 possible values. But in this example, this x1 random variable can take any positive real value. So now it is not distinct values, it is not disjoint discrete values, but it is taking a kind of a continuous value, any value in the interval 0 to 1 in the positive part of the real line. Okay, so there is some difference between these two random variables. Obviously, this is going to depend on what kind of sample space I am talking about, then what kind of function I am talking about. Based on that, this thing will be going to depend that whether the random variable going to take some discrete values or whether the random variable going to take some continuous values. Okay. Now, another important thing in this case maybe to study the following. Another important study is as follows. So, what is this? We may be interested. We may be interested not in the exact lifetime, but maybe that if interested in if a bulb was more than maybe 2 years or not. Okay, we may be interested in if a bulb was more than 2 years or not. If I am interested something like that, then instead of talking about exact lifetime, I maybe take a random variable x2, which is which is 1 if omega is greater than 2, and which is 0 if omega is less than equals to 2. So x2 takes value 1 if the lifetime is more than 2 years, and omega, the x2 is taking value 0 if the lifetime is less than equals to 2 years. This kind of function is called indicator function and normally denoted by the the notation is used is IA. So we later on we will use that IA equals to IA of a point X. At the point X, IA is a function. At the point X, it is 1 if X belongs to the set A, and 0 if X does not belongs to the set A. So that basically means this function x2 is basically nothing but I 2 to infinity of omega. Okay, I2 to infinity of omega, and this is x2. And when if I am only interested to know if a product lasts more than 2 years or not, I do not need to consider exact lifetime or everything in 0 to infinity, but I may talk about x2. And the important part with x2 is that in this case you see that x2 can take value 1 and 0, so it is taking kind of a discrete values, not like a continuous values like this example, like this one. Okay, so depending on different scenarios, I may need to talk about different random variables. Depending on the practical scenario, I need to define the random variable properly. Okay. Now, in this scenario, how we can talk about different probabilities? Natural question is that. Okay. So that we can do as follows. So now I am going to talk about something which the proof I cannot give you exactly, but I will going to give you proof or the definition I cannot give you exactly, but I am going to tell you some information about those things. Keep those things in mind. That's all. Okay. So exact definition, exact proof I cannot give in this in next few things. So first point I just want to mention here is that note that P of I Note that P of I, which is defined by e to the power minus P dt over I. Note that for I is a subset of S and I is an interval. For interval I, which is a subset of S, what is S? S was basically 0 to infinity in this case. So this Pi defines a probability function or a probability on the Borel sigma field on 0 to infinity. What is Borel sigma field? I cannot give you again the exact definition of the Borel sigma field, but keep in mind these following points. This Borel sigma field is a very important and useful sigma field in practice, and many situations the Borel sigma fields are used as the sigma field in practical scenarios. What is important about the Borel sigma field is that okay, it is useful and meaningful. Next point is that all singleton all singleton points in 0 to infinity belongs to Borel sigma field over 0 to infinity. The Borel sigma field is denoted by this notation. Okay, Borel sigma field is denoted by this notation. So Borel sigma field over 0 to infinity, all singleton points in 0 to infinity belongs to the Borel sigma field. Next point is that all intervals in 0 to infinity belongs to Borel sigma field. Note that when we are going to talk about probability, most of the time we talk about the probability of either singleton point or interval or some union of the intervals. Maybe I can talk about the lifetime of the bulb is more than 2 years, which is basically an interval. I may talk about the lifetime of the bulb between 1.5 years to 3 years. Okay? I can talk about the lifetime of the bulb is exactly equals to 2 years. So most of the time we are talk about either singleton point or kind of some interval. So as long as those things belongs to our concerned sigma field, I am done because I can talk about the probability of this set. But keep in mind that Borel sigma algebra or Borel sigma field over 0 to infinity is not equals to power set of 0 to infinity. So that basically means that there exists, it can be shown that there exist subsets of 0 to infinity which does not belong to the Borel sigma field. Though the construction of such events are very difficult and they do not we do not come across those kind of subsets of 0 to infinity in practice, and but there exists such kind of subsets of 0 to infinity which does not belong to the Borel sigma field. Okay, and the same, I mean, here we talk about the Borel sigma field on 0 to infinity, but we can talk about Borel sigma field over any interval. Even we can talk about the Borel sigma field over whole R. So if I talk about the Borel sigma field over interval AB, then any singleton point in the interval AB belongs to the Borel sigma field over the interval AB. Any interval in the interval 0 to 0 AB going to belongs to the Borel sigma field over AB, and so on and so forth. Again, that power set of the interval 0 to B is not same as the Borel sigma algebra over the interval 0 to infinity. Okay, so this information keep in mind. I am not going into exact, we cannot go in this course into the exact definition of the Borel sigma field, but keep these 3 points in mind and proceed. As we are not discussing the exact definition of the Borel sigma field, I also cannot able to prove that this pi actually defines a probability on the Borel sigma field. This one also take as a information and proceed. But what now I can do very easily, I can calculate different probabilities regarding the event, regarding the random variable x1. Note that if I try to find out what is the probability that x1 is less than or equals to x, so it is clear that this will be 0 if x is negative. Because if x is negative, for example, if I take x equals to minus 1, x1, if you remember that the definition we have used here for x1 is basically nothing but the lifetime. So lifetime cannot be negative. So I can tell that if small x is less than 0, then probability that x1 is less than equals to x has to be 0. Now for maybe x, now suppose I take small x equals to 1. So in this case, the probability that x1 is less than equals to x, which is equals to probability that x1 is less than equals to 1, and which is same as, because x1 is always greater than 0, so x1 is less than equals to 1. So that basically means that now, so that is basically I need to find out that x1 lies between 0 and 1. So lifetime lies between 0 and 1. Now if I use this one, see that this is the interval, I is the interval, here also I have a interval, so I can find this probability as integration 0 to 1 e to the power minus t dt, and that turns out to be 1 minus e to the power minus t. So in general, if my x is greater than 0, I can find out probability that x1 is less than equals to x, which is nothing but 1 minus, which is nothing but integration 0 to x, just like this. Here it is 0 to 1, so integration 0 to 1. Here it is 0 to x, so integration 0 to x, e to the power minus t dt, which is nothing but 1 minus e to the power minus x. Okay, I can find out the probability of x1 is greater than x, and this one is nothing but probability that x is less than x1 is less than infinity. So this quantity is x to infinity e to the power minus t dt, which is e to the power minus x. So in this way I can find out different probabilities. For example, I can find out what is x1 equals to x, and this is nothing but the integration. This is nothing but, you can think in this way, that it is basically probability that x is less than equals to x1 is less than equals to x, which is basically interval of length 0, and which is x to x e to the power minus t dt, which is 0. So in this case, if I try to find out the probability of any singleton point, it turns out to be 0. Though it is counterintuitive, but it is meaningful, because you can think it in this way. See, when I measure the lifetime cannot be measured exactly. That means it cannot be precision up to any decimal space in seconds. So that's why exactly one value, that probability could be 0, but when I think of some interval, I can find out those probabilities. Again, I can, if 0 is less than x is less than y, I can find out what is the probability x is less than x1 is less than y, which turns out to be x to y e to the power minus t dt, which is e to the power minus x minus e to the power minus y. Okay, so in this way I can find out different probabilities in this particular example. Let us little bit talk about x2. The definition of x2 was basically nothing but indicator of the set 2 to infinity. That means it will take value 1 if omega is strictly greater than 2, and if it will take value 0 if omega is less than equals to 2. And note that x2 can take values 1 and 0. So let us try to find out what is the probability of x2 equals to 0 and what is the probability that x2 equals to 1. So x2 equals to 0, what does this mean? This basically means that probability that x1 is less than or equals to 2. Okay? Because we take, if you just let me write the definition of x2 here, the definition of the x2 was 1 if omega is greater than 2, or this is equivalent to say that if x1 is greater than 2 and it is 0 if omega is less than or equals to 2, which is equivalent to write that x1 is less than or equals to 2. So that means basically x2 equals to 0. That basically means that x1 is less than equals to 2, and this probability is nothing but 0 to 2 e to the power minus t, which is 1 minus e to the power minus 2. Similarly, I can able to find out what is x2 equals to 1, which is nothing but probability that x1 is less than or equals to 2, which is e to the power minus 2. You can easily calculate, it turns out to be e to the power minus 2. Again, note that because x2 can take values 0 and 1, so probability of x2 equals to 0 plus probability of x2 equals to 1, that quantity turns out to be 1. Okay, clear? So in this case, if I know again the probability assignment on the constant sigma field, I can able to find out probability relating to random variables, different random variables. Okay, so again note that the one fact you note that which I am using again and again to find out that probability of the random variable x belongs to subset A, what I have to do, I have to basically find out the inverse image of the set A under X. And once I do that, I can find out the probability. Okay, clear? So this way the random variable is defined. The next thing we are going to talk about is something which is called the cumulative distribution function. So cumulative distribution function. In short, we will write it as CDF. Okay, in short, we will write as CDF. So you can understand from the definition, it is a function. So what function it is? The cumulative distribution function, generally denoted by capital F or some capital G. So cumulative distribution function of the random variable x is a function from the set of real numbers to the set of real numbers, and it is defined by, rather I write it in this way, from set of real numbers to 0 to infinity, and it is defined by f of x at the point x is nothing but probability that the random variable x is less than equals to small x. So the random variable x is less than equals to small x. This probability is called the cumulative distribution function. And you can understand for different values of small x, this probability can take different values. So it is a mapping from R to 0 to infinity. Note that in this case, it is very easy to understand that CDF, the cumulative distribution function, is defined for all real numbers. So when we try to write a cumulative distribution function, I have to write it for all real numbers x. And next point, as the cumulative distribution function is a probability, though here I have written that the codomain is 0 to infinity, but actually the cumulative distribution function for any particular value of x actually belongs to the set 0 to 1. So the range is basically the interval, the closed interval 0, 1. Okay? So not range, basically instead of 0 to infinity, I can take as the codomain is 0 to 1. Okay? So this point keep in mind. Now let us take some example where we calculate the distribution function. So this is a continuation of first example 2.1. So where basically we toss coins 2 times. So I have that S is head head, tail head, head tail, and tail tail, and we took that x is a random variable defined from S to R by x omega equals to number of heads in number of heads in omega, and also we have seen that probability that x equals to 0 is same as 1 by 4, probability x equals to 1 is half, and probability x equals to 2 is 1 by 4. Okay, these things we have seen. Now let us try to find out what is the cumulative distribution function of x. Finding out this is fairly simple. Again, note that I have already mentioned that when I am going to define a CDF, I have to define it for all real numbers. Okay, so let us start with some particular value. Suppose I first try to calculate what is the probability of, what is the cumulative distribution function of x, that is random variable number of heads at the point minus 1.5. So which is by definition probability that x is less than or equals to minus 1.5. Keep in mind that in the cumulative distribution function, this sign is less than or equals to, not strictly less than and equals to. Okay, so which is 0 because x cannot take negative value. Okay, so that logic I can extend, and I can write for any x less than 0, f of x at the point x, which is by definition probability capital X less than equals to small x, will be 0. Let us consider now the positive values of x. Again, let us take one particular example. Suppose first we try to find out what is the distribution function of x at the point 1.5, which is by definition x is less than or equals to 1.5, and x is less than 1.5. Rather first consider, okay, x is less than, let us consider this. So x is less than equals to 1.5. That basically means that x is equals to either 0 or x is equals to 1. Note that because only these 3 points have some positive probabilities, that means x is less than equals to 1.5 is same as the probability that x equals to either 0 or 1. And this probability I can find very easily because it is 1 by 4 plus 1 by 2. Note that x equals to 0 and x equals to 1. These two events are disjoint events. So probability of the union, or is union, probability of the union can be written as the sum of the probabilities. Okay, so I can find out this, and this turns out to be 3 by 4. Similarly, if I try to find out the probability of 0.5, which is basically x is less than equals to 0.5, in this case only possibility is that x equals to 0, which turns out to be 1 by 4. And if I try to find out the probability maybe 2.4, that is probability that x is less than equals to 2.4, which is probability that x equals to 0 or x equals to 1 or x equals to 2, and this sum of these all probabilities is 1. Okay, so I can extend this one again, and what I can write is that for 0 is less than equals to x is less than 1, f of x at the point x, which is equals to probability that x is less than equals to x. So when x lies between 0 and 1, only for this scenario is something like 0.5. So only possibility is that x equals to 0. So only possibility here is that x equals to 0. So this value is 1 by 4. Note that I do not write the equality here, because if I keep the equality here, then there is a problem, because if x equals to 1 I take, then basically there will be two possibilities, x equals to 0 and x equals to 1. So probability will get changed. So that's why that in this side I have put equality, but in this side I do not put the equality. For 1 is less than equals to x is less than 2, the distribution function at the point x will be nothing but probability that x equals less than equals to x. Now I have two possibilities, that x equals to 0 or x equals to 1, and this probability turns out to be 3 by 4. Similarly, for 2 is less than equals to x, f of x at the point x, if you take any value greater than equals to 2, then all the possibilities come inside the interval x less than equal inside the interval minus infinity to x. So that basically means that now it turns out to be 1. Okay, so that means that in this case, the cumulative distribution function is the CDF is given by f of x at the point x equals to 0 if x is less than 0, 1 by 4 if 0 is less than equals to x less than 1, 3 by 4 if 1 is less than equals to x less than 2, and if it is x is greater than 2, it turns out to be 1. Okay, so this is the complete cumulative distribution function, and note that we have defined, we have write the cumulative distribution function for all real values x. Okay, clear? I hope this is clear with everyone. Okay, let us take the next example. Next example I am keeping, you can just check, which is basically if I throw a die 2 times and x is basically the sum of the outcomes. So x is basically I plus j, as we defined earlier. What is, we have seen what is the cumulative distribution function that is given in the note, and just check it. Obviously, in that example, you will show that so let us just see here that in this case, actually we will have lot of cases, but the calculation is fairly easy. Just complete it. I'll not go into that. It's your duty to complete it. Okay, let us now talk about the example 2.6, which is a continuation of the example 2.3, which is basically the lifetime example, the lifetime of the bulb example. Okay, so in this case, if I try to find out the cumulative distribution function of x1, it is very easy to find it out. The reason is basically nothing but that example 2.6, which is continuation of example 2.3. So in this case, x1 was lifetime, and the probability assignment we use is that integration over I is the interval e to the power minus t dt. I is the interval in the positive part of the real line, and you can see that in this case, if I try to find out what is the distribution function of x1, very easy to find out, because again for x is less than infinity, f of x is less than 0, f of x is equals to probability x1 is less than equals to x, f of x1 x at the point x is probability x1 is less than equals to x. As lifetime cannot be negative, this probability will be 0. And for x is greater than equals to 0, the distribution function at the point x1 x is equals to probability that x1 less than equals to x, which is basically the probability that 0 is less than x1 is less than equals to x, and which is nothing but the integration 0 to x e to the power minus t dt, which is 1 minus e to the power minus x. Okay, so in this case, the CDF of x1 is f of x1 x is 0 if x is less than 0, it is 1 minus e to the power minus x if x is greater than or equals to 0. Okay, I can find out what is the distribution function of x2. Remember that x2 was basically the indicator function of the interval 2 to infinity, and we have seen that x2 takes value 0 with probability 1 minus e to the power minus 2, and x2 takes value 1 with probability to the power minus 2. And in this case, again, you can find out the CDF very easily of x2 is f of x2 x. Again, x2 do not take negative value, so 0 if x is negative. If 0 is less than equals to x is less than 1, the probability is 1 minus e to the power minus 2, because when x lies between 0 is less than equals to x is strictly less than 1, then only possibility is that x2 equals to 0. That's why the probability is 1 minus e to the power minus 2. And if x is greater than equals to 1, then both the possibilities come inside the interval minus infinity to small x, and so the probability turns out to be 1, which is basically sum of these 2 points. Note that this is the sum of these 2 probabilities, not the individually this probability. Okay, fine. So I hope that these examples are okay with everyone. So in this lecture I stop here, and in the next lecture we are going to discuss some of the properties of the cumulative distribution function.